Hello everyone from Math 1340 Statistics. It's Professor Wenson here again with a video for your KnewtonAlta homework, section 3.1, part 2, an introduction to probability. So again, hopefully you've read through section 3.1 in your OpenStax book already and watched some of the other videos I provided for you in Canvas. Before you and practice some problems, taking some notes, organize those notes, all that good stuff before you start watching this. And this is hopefully just a nice little guide for you to take you through the assignment when you do it on your own. Alright, so I'm just going to start right into it. And you're not going to see the word preview, I keep saying that. Got your mastery bar, you can see your objectives. There are 3 objectives in this particular assignment. The first one I'm seeing here is describe and create basic probability distributions. So as I've been saying every video, when I come across a new objective, I would recommend clicking on More Instruction. And let me read through some of this for you. Now there is a video. I'm not going to play a video here within the video, but you've seen frequency distributions, where you have your classes and then frequencies. You've seen that before, right, in an earlier chapter. In this section, we're also now going to be talking about probability distributions, which will be you'll see a table. Now, we're going to be doing probability distributions for discrete random variables. Remember, discrete versus continuous, right? Discrete could be counted as opposed to continuous, where it was measured. And if you don't remember the difference between discrete and continuous, please go back to chapter 1. So in this section, when we create what's called a probability distribution, it's going to be like a frequency table, a frequency distribution. And yeah, you'll see here. All right, so I'll just go through an example that they give. So for this example, right, in this video, well, the video that you watched, I'm not watching it. Some of the distributions were left as frequency distributions. In order to convert a frequency distribution into a probability distribution, first count the total number of observations, right? The sum of the frequencies. How many values are there? How much data do you have? What's the size of the sample? Then divide each individual frequency by its sum. So basically, if you have a frequency distribution, the corresponding probability distribution is just made up of relative frequencies, and hopefully you remember what those are, right? It's basically what percentage is in each row, what percentage of the data is in each class. So here's an example, right? This table here shows the frequency distribution for the candy color of a bag of M&Ms. The first column is the candy color, the second column is the frequency. So like in this particular bag that was sampled, there were 17 brown M&Ms, 18 red, 7 yellow, and so on, for a total of 55 M&Ms in the bag. So a probability distribution just gives you the same categories, and this variable called x is just candy color. A random variable is just whatever is being recorded. So x here represents candy color, M&M color. And the right column is, remember this notation from section 3.1 part 1, this is the probability of x. Right? So what's the probability of getting a certain candy color in this sample? So I see it's just simply relative frequency, right? The probability of selecting a brown M&M out of this bag is 17 out of the 55, right? Or approximately 0.31, 31%. The probability of picking a red M&M out of this bag is 18 out of 55, right? See the fraction there, approximately 33%, and so on. And just as with relative frequency distributions, right? Remember percentages, fractions. the sum, right? The sum of all the probabilities, all these percentages, all these fractions, all these decimals. The sum of the probability column should be equal to 100%, right, or 1. Right. And be careful too, right, in the probability distribution, note that all probabilities are between 0 and 1, and that the exact value of probabilities all add up to 1. Right? Now these add up to 1.01, but due to rounding, right? So if these are all because these are all rounded. So when you add them up, if you were rounding, they might add up to 0.99 or 1.01. As long as they're very, very, very close to 1, you probably made the distribution correctly. Another thing, right? The probabilities are between 0 and 1 only, from 0 to 1 only. You've seen this earlier. So you're not going to see probabilities greater than 1. You're not going to see probabilities that are negative, less than 0. And one more time, in a proper probability distribution, the sum of all the probabilities is going to be 1, or 100%. Okay, so an example here. So a student opens a bag of her favorite candy and counts how often each color occurs. The results are shown below. So I'm given this frequency distribution, and I'm asked to construct a probability distribution for this particular frequency distribution, this particular bag of candy. So X here represents the candy color, and then you see this P of X, right? What's the probability of selecting each color of candy from this bag? So it's just, again, just relative frequencies. So I would add up, you can pull a calculator out if you want, but add these up. How many candies are there in the bag? So there are 50, right? There's 25 here, and 14 and 11 make 25 again. There are 50 candies. And they want us to round all answers to 2 decimal places, so let's write them as decimals. So what's the probability of selecting a yellow candy from this bag? It's 12 out of the 50, which as a decimal would be 0.24. 0.24. That's 12 out of 50. What's the probability of selecting a red candy? 13 out of 50, out of the total, or 0.26, 26%. What's the probability of selecting a purple? 8 out of 50, or 16%, 0.16 as a decimal. The probability of selecting a green candy is 6 out of the 50, or 12%, 0.12. And finally, the orange, 11 out of the 50, or 22%, 0.22. And add these up. You have 50% here, then 66, 78, 100. Right? And 100%. They all add up to 100%, or they all add up to 1. Right? And they're all positive. They're all between 0 and 1. So this is a perfectly valid probability distribution that has just been completed here. And again, they go through the same explanation. You count up how many candies are there, what's the total number, what's the size of the sample, and then you're calculating probabilities, or in this case, basically relative frequencies. Right. So another one. Now the question. Now this time, they're going horizontal instead of vertical. Oh no! Don't worry about. They can go horizontal or vertical. These tables. So again, X will represent some variable, whether it be candy color or height, weight, numbers of cars, I don't know, whatever it represents. So here are the possible outcomes. Right? So the possible values of X are 2, 4, and 6, and they're stating the probability of having 2, X be 2 is 1/5. The probability of x being 4 is also 1/5, and the probability of x being 6 is also 1/5. Now the question is, or they're asking you to, determine whether or not the distribution is a probability distribution, and select the reasons why or why not. Now, look at all the probabilities. They're all, from 0 to 1. That's not a problem. But remember the other thing is that they have to add up all the probabilities. The sum of the probabilities of all the outcomes has to add up to 1. Add these up. 1/5 plus 1/5 plus 1/5 is 3/5. That's 0.6. That's not 1. Meaning that this table doesn't take into account every possibility. It needs, in order to be a proper probability distribution, it must take into account every possible outcome. All the probabilities need to add up to 100%. So the given distribution is not a probability distribution since the sum of the probabilities is not equal to 1. And it says select all that apply, so let's see if these other ones also would make sense as to why this is not a probability distribution. The given distribution is a probability distribution. No, it is not. It is not a probability distribution since at least one of the probabilities is greater than 1 or less than 0. Well, no, these are all 1/5. That's between 0 and 1. And the given distribution is, well, no, it isn't. So that's the only reason there that it is not a valid probability distribution. Okay. Here is a same objective, same kind of question. X represents some variable. Here are the possible outcomes for x. Here are the possible values of x, 1, 2, and 3. And then below it we have the probability of x being 1, is 1/4. The probability of x being 2 is a half. The probability of x being 3 is a quarter. And we're asked again to determine whether or not the distribution is a probability distribution and state the reasons why or why not. So all the probabilities are fine. They're all from 0 to 1. Right? Nothing bigger than 1, nothing less than 0 in the probability row here. Add up the probabilities. Now this is 1/4. Now remember, when you add fractions, you need a common denominator. Or you can change them to decimals if you want. So I got 0.25 plus 0.5 is 0.75, and then plus 0.25 again is 1. So this looks like a perfectly valid probability distribution. So the given distribution is a probability distribution since the probabilities lie inclusively between 0 and 1. And also this reason too. Right? The given distribution is a probability distribution since the sum of the probabilities is equal to 1. Right? It says select all that apply. These both apply to contribute to the fact that this is a valid probability distribution. And then these say it's not, but we've said it is. So these are it. Okay. Again, the explanations, please read those. Make sure you make sense of them. Another one, same kind of question. Now this is a capital X, no big deal. It can be any letter you wish. So here's the variable x, all the possible values of the variable x, 0, 1, and 2. And then the probability of x being 0 is 0. Now remember, that's fine. You can have a probability of 0. That just means that that x being 0 will never happen. Right? A probability of 0 means that that is never going to happen. Probability of x being 1 is 1/3. The probability of x being 2 is 2/3. So yeah, all the probabilities are from 0 to 1 inclusively, and that's happening here. And let's add up the probabilities. 0 plus 1/3 is 1/3, plus 2/3 is 3/3. That's 1. This is a perfectly valid probability distribution because all the probabilities lie inclusively between 0 and 1. That is happening. And the sum of the probabilities is 1. That is happening as well. It is a probability distribution. Okay. So that's really all you're looking out for in this first objective. And also, how to calculate probability, right? You take how many divided by the total. All right. And next is compute probability with equally likely outcomes, meaning every outcome in the sample space. Hopefully, remember in the section 3.1, part 1, the sample space of an experiment was the list of all possible outcomes. And here we're going to look at the situations where all those possible outcomes have the same likelihood, right? They're equally likely to occur. So yeah, first time I'm seeing this objective, I'll click on More Instruction, show you what that looks like. And again, there might be some videos or whatnot. I'll leave those to you to watch. But here we got some reading. Compute probability with equally likely outcomes. So probability of equally likely outcomes is a measurement of a particular outcome compared to all possible outcomes in that sample space. So for an event A, and you've seen the word event in section 3.1 part 1. For an event A, we would say that the probability that A occurs is equal to the number of ways A can occur, or the number of outcomes in event A, divided by the total number of outcomes in the sample space. And again, this needs to be equally likely outcomes. Everything in the sample space has the same chance of occurring. But it's the way number of ways A can happen divided by the total number of outcomes in the sample space, the total number of possible outcomes. So, for some experiments, all outcomes are equally likely. This means that each outcome of an experiment occurs with equal probability. Some examples of this are rolling a fair six-sided die. Right? Each side has a 1 in 6 chance of occurring. Right? So every outcome is equally likely. Drawing a play card from the standard deck of 52 cards. Right? So every card has a 1 in 52 chance of being selected. Or flipping a coin, right? Heads and tails both have a 1 out of 2 chance of being selected. So these are examples of experiments where every single outcome has the same chance of happening, equally likely. Right. Remember, just because an event has a certain probability does not guarantee that it will happen. Right. If we flip a coin 2 times, we may end up with 2 tails, T and T, and never see a heads, even though we know that it is part of the sample space. Even if we flip a coin 100 times, we may still never see a head, even though that's very unlikely, right? Flipping a coin 100 times and getting all tails. So the theoretical probability of any outcome is the long-term relative frequency of that outcome. Theoretical probability is what we expect to happen, not what actually happens. Right, so the example here, if you flipped a coin 100 times, you'd expect about 1 in 2. You'd expect about 50 of these 100 times to be heads and about 50 of the 100 times to be tails. Again, that doesn't mean that's what's actually going to happen, though. Right? So probability gives us kind of what we expect to happen, not what actually happens. An example they give here too is as we repeat the coin toss over and over and over again, we expect that out of every 2 flips we will have a head at least 1 time. Again, doesn't mean it's going to happen, but we would expect that to happen, something close to that. So to calculate the probability of an event A, when all outcomes in the sample space are equally likely, that is huge right there. This formula that's up here is only good really when all outcomes in the sample space are equally likely. Every possible outcome of the experiment has the same chance of occurring. Then we can say this is how we calculate the probability up here with this formula. We can use the theoretical method of equally likely outcomes described below. The number of ways A can occur divided by the total number of outcomes for the probability that A occurs. Right? Okay. So they have an example here. A referee flips a fair coin once before a sports game. awarding the ball to the team that guesses the correct coin face showing, heads or tails. What is the probability of flipping a head? Right, now the experiment here is, again, flipping a coin once. There are two outcomes, heads, tails, and they're both equally likely. Right, they both have the same chance of occurring. And one of those is heads, 1 out of the 2. Right? So you see the probability of flipping a head, 1 out of 2, 1/2. Pretty simple one. And I'll give you another example with dice. Cool. All right, we'll do some problems here in a second. All right, so here, you roll a standard die, right, with 1 through 6 on it. Let A be the event that you roll an odd number. What is the probability of event A? All right, so I'm going to pull up some paper here, just in the corner of the page here. Not too big. Hopefully you can see this. So what's the, the experiment here is rolling a die. The sample space then is just simply rolling. I mean, they have it right there in the problem. It's these outcomes, right? It's the list of all possible outcomes when I roll one die. Roll 1, 2, 3, 4, 5, or 6. And every single one of these, as we've mentioned, has the same chance of occurring. Right? These are all equally likely. All right, I'll write that here. Right, these are equally likely outcomes. I'll just say equally likely. Now they told us event A is the event that you roll an odd number. So remember, an event is just another list of outcomes. Now rolling an odd number would be rolling a 1 or a 3 or a 5. So here are the outcomes that show up in event A. Right, so then they're asking, what is the probability of event A? Right, so that's this P, and then in parentheses A, right, the probability of event A. Now, since my sample space has equally likely outcomes, right, none of these have a greater chance of occurring than anything else. They all have the same chance of occurring. Since my sample space is made up of equally likely outcomes, I can very simply calculate the probability of A. It's how many outcomes are in A, 1, 2, 3, right, the 1, the 3, and the 5, divided by the number of outcomes in the sample space, right, the total number of possible equally likely outcomes, that's 6. So the probability of rolling an odd number is 3 out of 6, which you're going to have to reduce the fraction, I believe. 1 out of 2, right, 3 goes into 6 twice, 50%. Now they ask you to give your answer as a fraction, so 1 out of 2, right, 1/2. Pretty simple, that one, I believe. Right. Now you can try 3 out of 6. I'm pretty sure that they accept unsimplified fractions, but I would recommend just to be safe, simplify your fractions. All right, here's another one. A professor gives a surprise quiz with one multiple choice question. One. There are 4 answer possibilities, A, B, C, and D. What is the probability that you randomly guess and select the correct answer? So here, the sample space, now there's only one multiple choice question, only one question being asked. The sample space then is I select A, I select B, I select C, or I select D. The right answer could be one of these 4. And there's an equally likely chance that each one has a quarter of a chance, right? And that's the probability, right? Because the probability that you get the answer correct, the numerator is how many ways can you get the answer correct? Well, only once. There's only one correct answer. Divided by, and then how many total possible outcomes are there? 4. I mean, this is very simple. I believe this one, and it says enter again as a fraction, 1 out of 4, 25%. All right, so here we go with another question. Same objective. When a fair coin is tossed 3 times, what is the probability that all 3 tosses are heads? Now, they give us the sample space. Right? When you toss a coin 3 times, all 3 can be heads, all 3 could be tails. The first one could be a head, then the next 2 tails, the first 2 heads, then the last 1 tails, the first 1 tails, the next 2 heads, the first 2 tails, the last 1 heads, heads, tails, heads, tails, heads, tails. There are 8 outcomes. Look at this. All right, that's 8 total possible outcomes. So that's going to be my denominator, 8. The numerator is how many times does the event they're talking about occur. The question is, what is the probability that all 3 tosses are heads? How many ways does this happen? Once. Right there. All 3 heads. So it's 1 out of the 8. Very, very simple. And again, just it doesn't say enter as a fraction, so you could enter this as 1 over 8 or 0.125, 12.5%, but it's easier with the fraction. Just 1 out of 8. Very, very, very easy, I think. So another one, same objective. The census is a survey of the population that gathers various details about individuals, such as age, the age of every individual. This survey observed that 155 out of every 200 people were 18 years or older. So determine the probability of randomly selecting a person that was 18 years or older. So how many ways did that happen? There are 155 of those people they're telling us right here, out of the 200 total people that were surveyed. Very, very simple. Now let's see. I'm going to type this one in as just simply 155 out of 200 and see if it accepts unsimplified fractions. Hey, look at that, it does. So if you want to save a little time, you could just enter unsimplified fractions and it looks like it takes it. Very, very easy, that objective, I believe. And then the final objective is use what's called the complement rule for probabilities. All right, so new objective. Now you've seen the word complement before in section 3.1 part 1. Remember, the complement of an event was not that event, right? And so if an event was called A, remember the complement of the event was called A prime. It had an apostrophe on it. So again, first time I'm seeing this objective, I'll go show you the more instruction here. I think there's a video, yeah. But here's the rule you need to remember. Right here. Or here. I mean, these are the same rule. You just subtract one thing from both sides. So remember, the complement of an event A is the event not occurring. And is denoted by that A prime, right? A with the apostrophe. So remember, for any event A, either A or A prime must occur, right? Because either something happens or it doesn't, right? Either A occurs or it doesn't. So the probability of A occurring plus the probability of A not occurring will always add up to 1. This is for any event. The probability that it occurs plus the probability that it doesn't will always add up to 1. Right, and then this complement rule is just taking this rule here and subtracting the probability of not A from both sides. Right, so if you just remember that the probability of an event plus the probability of that event not occurring must always add up to 1. If you remember that, you'll have the complement rule down. All right, so let's get to our problem. So here, there were 2,626,418 deaths in 2014 according to the CDC. 614,348 of these deaths were caused by diseases of the heart, and 136,053 were caused by unintentional injuries. All right, what is the probability that a death in 2014 was not caused by diseases of the heart or unintentional injuries. All right, so again, I'll pull up some paper here. So let's say event A is, a death caused by, is the event that death was caused by heart or injuries. And I'm not going to write out all those words. All right. So the probability of A occurring, remember, is the number of ways A happened. So how many deaths were caused by hearts or injuries? Remember, it's or, so you include both. So the heart problem injuries were deaths were 614,348, and I'm going to add to that the ones that were caused by injuries, 136,053. All right, and then we'll get the total there. Out of the entire amount, right? Out of all the people that died, out of all the deaths, 2 million. So in the denominator, I have 2,626,418. Right. And we'll approximate this. I'll bring my calculator up and do this. So this is kind of hanging over it here. I'll maybe scoot this over a bit. Maybe you can see that right there. Perfect. All right. So let's see what the numerator is first. All right, what's 614,348 plus the injury deaths, 136,053. All right. So the numerator here is 750,401, and then we're dividing this by 2,626,418. All right, now this gives us the probability that a death was caused, right? Death was caused, is caused, right, by the heart problems or injury, unintentional injuries. So if I want the number of deaths that weren't caused by this, the probability of not A prime, right? The A prime then would be the death is not caused by these heart problems or injuries. All the rest of them, right? 750,401 were caused by these two. All the rest of them were not caused. So what I'm going to do is I'm going to subtract. I'm going to take this number here, this 750,401, and subtract it from the 2 million something. I'm going to take 2,626,418 and subtract that previous number. Right, so 1 million, so the numerator here is 1,876,017. That 1,876,017, that's how many deaths were not caused by the heart problems or injuries. And then for this probability, the probability that it doesn't occur is divided by a total, divided by 2,626,418. All right, so I'm going to divide this, take this number I have here, divide it by the 2,626,418. We're getting approximately, and they asked us to round to the nearest, enter your answer as a percent. All right. So let me pull this down. So on the calculator, I'm getting this. So the probability of these deaths not being caused by the heart or injuries is approximately 0.7142 ... Changing this to a percentage, you move the decimal place. So this is 71.428. Move the decimal place to the right twice. ... percent. All right, remember, percent just means divided by 100. If I divide this by 100, it would take me right back to that. And to the nearest tenth of a percent. All right, so this is 71.4%, but then the next number is a 2, so I just keep it as 71.4. All right, so I'm going to enter here 71.4%. The probability that the death, a death was not caused by disease of the heart or unintentional injuries. And if this is 71.4, right, if this is 71.4%, then the probability that they were caused by the heart or injuries is going to be approximately 28.6%. Because remember, this rule here, the probability of an event plus the probability of not that event has to be equal to 1 or 100%. Right? So the probability that the deaths were caused by those two things is about 28.6%. Then the probability that they weren't is, as we saw, was 71.4%. All right, let's see if that worked out. Great. And I go through again the explanation here and all that. And that's pretty much what the rest of this is like. Here's an event. What's not that event? Right? What's the probability of not that event? So here there are 26 cards in a hat, each of them containing a different letter of the alphabet. If one card is chosen at random, what is the probability that it is not between the letters L and P inclusive? All right. So this time I'll go to some paper. I'll blow it up. I'll make this one a little bigger. So my denominator is going to be 26. Now again, let's say event A, I'll just say event A is selecting a letter between L and P. So this is selecting L, M, N, O, and P, right? Including them, it said inclusive, L, M, N, O, P. So the probability of doing that, the probability of selecting one of these letters is 5 out of 26, right? Because there are 5 of these letters out of the 26 in the alphabet. So that means the probability of not doing this must be 21 out of 26, right? Because if you add these up, right, basically subtract this from 1, right? This is 1 minus 5 26ths, and get a common denominator. That'd be 26 26 minus 5 26. Be 21 26, right? The other 21 letters of the alphabet are not from L to P. And that's what we were being asked. We're asked what's the probability that the letter we select is not between L and P inclusively. So hopefully that made sense. Again, the probability of an event plus the probability of not that event must be equal to 1. So I just enter as a fraction, 21 out of 26. Here, a campus contains buildings numbered 1 through 70. What is the probability that a student will enter a building that is not a multiple of 12? And this time it asks us to reduce the fraction, see? Reduce the fraction. Sometimes it didn't, and you could get away without doing it. All right, so 1 through 70, that means I'm going to be dividing by 70, right? There's a total of 70 buildings. What's the probability that we're entering a building that's not a multiple of 12? So again, I'm going to have event, I'll call it T for 12. How about is multiple of 12? Is a multiple of 12. I'll start with that. So that means I could enter building 12, building 24, building 36, building 48, building 60, and that's it, because after that it's 72, which is too big, right? There are only 70 buildings. So the probability of entering a building that is a numbered multiple of 12 is 5 out of the 70 buildings. Right? Meaning that the probability of not doing this is, the other 65, right? The other 65 buildings are not a multiple of 12. 65 out of the 70 buildings. And they did ask us to, reduce 5 goes in each of these, 5 goes into this 13 times, and goes into this 14 times, right? So 13 14ths, and this is only 1/14th, right? If you divide each of those by 5. And again, see how they add up to 1, right? The probability of an event plus the probability of not that event should always add up to 1. So with the reduced fraction, the probability of not entering a building that's a multiple of 12 is 13 out of 14. 13/14. Right. I've probably got one more here. So here, pictures from an artist. It's basically the same. Right. At 1 through 60 this time. Right. The number 1 through 60. What's the probability that the artist will choose a picture that is not a multiple of 13? Well, let's think of the ones that are a multiple of 13. So I'm just going to do this out loud. You have 13, 26, 39, 52, and then you're too big. So 13, 26, 39, 52, that's 4. 4 out of the 60, or 1/15th, is a multiple of 13. So the other 14/15ths, right? The other 56/60ths. Now here it doesn't say reduce. Oh, it does say reduce the fraction. Okay, so 14/15ths are not. 14/15ths of them are not a multiple of 13. Okay, and I believe that is all. All right. So again, the 3 objectives. Hopefully, again, watching this video, you're not going to see things in the same order that I do. You might not even see the same exact problems that I do, but the objectives are the same, the materials the same, the instructions the same. The types of problems you're going to see are the same. They might just have different numbers. And how you would approach them would be the same. The rules you're going to use and how you would go about doing them. All the same. So hopefully you can flip around back and forth, flip through this video, and use it as a nice guide for you when you're doing the assignment on your own. All right, and thank you very much for watching.